Hi guys, how we doing? Welcome back to another video. So I'm now going over voltage regulation. I'm testing out this HP2001, which is a brushless DC motor and a DC motor, brushed DC motor coupling pair. So you can see there. And my job, well, I've got this from work, and I need to basically go through and update the curriculum with some of the changes that have happened. Which, from the looks of things, it just looks like they've just added potentiometer to control the speed of the brush DC motor, and also a switch to control the direction. So in this video, we're going to be going over voltage regulation. If you've been following along, I've been trying to make it fit all on one board. That won't work for this one. If you have a look at this schematic here on the curriculum, it's pretty hefty. So what we have is we've got our 12 volt coming in over there, and then we've got this microcontroller being powered by that 12 volt. And then we've got a potentiometer on input C of this microcontroller. So this potentiometer, if you can see here, can you see? You can see here. It's controlling the speed of this motor. So, alright, so we're at 76 PWM. As I rotate this, then that changes the speed. So this microcontroller essentially is just reading in this input from this potentiometer over here. And then that controls the speed. So anyways, cool. So this controls takes the input from my potentiometer and then outputs here to this MOSFET, onto the gate of this MOSFET, and then the MOSFET is driving. This is a flyback diode, and then the MOSFET is the one that is driving from the 12 volt supply up to this brushed DC motor, and this brushed DC motor is then driving this brushless DC motor, which is then generating a 3-phase waveform. And then that is then being put here across this full bridge rectifier, which we did in the last video. And then that should then give me a DC voltage smoothed with this capacitor here. So smoothing capacitor, that should then give me a nice clean DC voltage across here. So if I just stick my meter across it in DC mode, we should get something like 2 volts, I guess. Minus away, so 2.8 volts DC. And if I go on to AC, do I get anything? Like just a random variant, I guess, voltage. If I stick onto the output here of this motor before it's rectified, phase to phase, I get a nice solid 3 volts. So I've got a solid 3 volts coming out from this solid 3 volts coming out from here, being generated by that, since this is essentially acting as a dyno. So it's quite cool actually. The last few worksheets, they've come together nicely. And you know, this is the really cool thing about this Locktronics. It's pretty amazing that you've got 2 boards there. Yeah, anyways, it's just, yeah, I'm very much impressed. This is a very good product from Matrix. I could easily see myself spending 20 hours learning. There's actually so much to learn here, and I'm just kind of glossing over a lot of it. Like, I don't really even understand really this flyback diode. Yeah, so cool. Let's just jump, I guess, into we'll read the worksheet and then just see if there's anything. It does get a little bit more complicated. This circuit then changes a bit, so let's just go through and just make sure there's no changes I need to make to the curriculum, and then also we'll just cover anything new or anything that we can learn in the video. So power generators, let's turn this down, this motor's a bit loud. So power generators need to regulate their output power, which varies greatly with rotational speed. That makes sense. There are 3 approaches. Use electronics to regulate the output. Use electronics to regulate the output. Is that what we're doing here? I don't know. I don't think so. I'm guessing this is like the alternator. So this is simulating the car's alternator, I think. Anyways, so there are 3 approaches. Use electronics to regulate the output, dissipate excess power as heat, or use an inverter to modify the output. The first part of the worksheet shows you the problem that the output voltage varies with motor speed. Okay, so we can confirm this ourselves. So if we take, I think we already have confirmed this in a previous video, but if we just go on to DC there, and then go across our output resistor here. So I'm on DC. I guess it's not a constant speed right now because it's so slow. So I'm getting like, I don't know, 50 millivolts. So I go crank it up a bit. I'm getting 500 millivolts. Crank it up a bit. About 1 volt. Crank it up a bit. 1.7 volts. Crank up a bit. 2.7 volts. So I guess what this is saying is that if this was a car's alternator, the voltage would be varying a lot, and that I guess wouldn't be a good thing. Maybe. Yeah. Anyways, so the photograph shows a voltage regulator. Cool. Oh, it says the second part looks at the first part of the worksheet shows a problem that the output voltage varies with the motor speed. The second part looks at an electronic solution. Cool. So set up the circuit shown on the next page. The DC motor here drives a brushless DC motor, which generates a three-phase electricity. The 1K resistor represents the load on the system. Select program 14, which I've done on there. Connect an oscilloscope to monitor the power supply to the DC motor. I'm not going to do that. Adjust the pot to control the speed. Done that. Observe the waveform applied to the DC motor as you do so. Use a multimeter to measure the voltage generated across the load for the drive levels of 20, 40, 60, 80, 90. That's quite, yeah, this is all like quite a good learning experience for a student. So I'm going to skip all that. So we bought that. So what's next? The output depends on the speed of the DC motor. In a vehicle, this is a problem as the lead acid battery needs a fixed charging voltage. The solution, add a feedback loop to control the speed of the motor at a set level. So I'm still not sure what speed of which motor are we referring to in a car here. I assume what we're referring to is the speed of the alternator, which is charging the battery when you're driving the car. That's what I'm assuming, but I'm not too, this hasn't been too clear on that. So the solution, add a feedback loop to control the speed of the motor. So what are we doing? Are we speeding up the alternator, I guess? Add a feedback loop to control the speed of the motor at a set level. In the following circuit, this feedback signal is carried by the orange cable. Orange. There's no orange cable unless they just mean just that row there. So, all right, let's modify this circuit a bit. So we've got some 10 ohm resistors going here. We've got a 1K resistor going there. 10 ohms. Where do the 10 ohms go? How many are we doing? 3. Alright, I'm a bit confused here. So 1K going there. 3 10 ohms ones going there. Gotta join them all together. I mean, this is insane, right? Like, I'm doing this live whilst the circuit's running, which shows, like, you know, look at how safe this thing is, and look how quick and easy it is to just plug stuff in. It's honestly, I am bloody amazed at the quality of this product. This is good. It was a pain in the ass to install all these pillars by myself, but we won't get into that. All right, so I've done that. It does also say that there's this pink one here that I gotta install. Okay, that's something you could easily miss. And do I even have enough of these carriers? I'm running low. I'm scrounging here. All right, another one. I think I might be out, so it must mean that I'm not to use as much. So up here, I gotta take out that potentiometer. I'm putting a 2.2K. Oh, that started to run. Take that out. Put a 2.2K there. I don't know why that's running. It's interesting. And then what am I doing? A 1K one there. And then that there. That one there. So is that the whole circuit? 2.2K, 1K. There. I think I'm good there. Alright, so that's enough. I've got one spare. So now we need some jumper cables. So we are jumping from, I guess this is the output of the rectified voltage, and we're going into a voltage divider here. And this microcontroller is reading that voltage across that 2.2k, I guess. Is that everything? I think that's everything. So what happens now? But it says it's got a 0%. What do I do? Is something supposed to be happening? Alright, it's not running for me right now. What did it say? Have I read everything? The output depends. The solution: add a feedback loop to control the speed of the motor at a set level. In the following circuit, the feedback signal is carried by the orange cable. I mean, for one, there is no orange cable here, so it must just mean this bank here. So build the second circuit shown on the previous page, but without any of the links colored orange. Oh, that's why you should read. All right, so without any of the links colored orange. So pop all these out. As before, the speed of the motor is determined by the voltage at the input terminal C. This time, however, that voltage is fixed by the 2.2k and 1k resistors. Previously, it was variable, adjusted by the pot. Select program 16 motor feedback. There we go. So, program 16 this time. Again, I'm not the best at reading instructions, if I'm honest. And I also did spend all of today reading bloody Siemens manuals. Alright, so we've got some action right now. So that's good. Connect an oscilloscope to monitor the power supply to the DC motor using the same settings as before. Connect a multimeter to monitor the voltage. So I'm not going to do the oscilloscope stuff. I will do the multimeter stuff. So connect an oscilloscope to monitor. Connect a multimeter to monitor the voltage across the output smoothing capacitor. Would that be AC or DC? I don't know. Smoothing capacitor. That's going to be rectified DC, isn't it? So. Yeah, so we're gonna get nonsense on AC, so it'll be rectified DC. So we have a 1.5, 1.7 volts. Then in turn, add the orange links to change the load by adding one 10 ohm resistor at a time. Okay, so one link. Ah, nice. 1.5 to 1.9. 1.8. 1.6. So now, so it was like fluctuating a fair bit this way, and then now it's just like a steady 1.69. That's cool. So here the micro ECU uses the DC motor to motor speed to control the voltage generated by the three-phase brushless DC motor. When this voltage falls, the micro ECU increases the drive to the DC motor. When it goes up, the micro ECU reduces the drive. This is a good example of a closed-loop feedback system. Car alternators achieve the same result by varying the field coil current in the alternator. Use the internet to investigate alternator regulator circuits. Write a summary to outline your findings to one of your fellow students. I mean, what an absolutely brilliant bloody worksheet that one was. That is amazing. Now, did I understand it? No. But you know, this is not to be used. You know, a student's not meant to take this home and figure this out themselves, are they? They're meant to build this, you know, even in a group of 2 or 3 of them, and then write down all the observations. And they have a teacher at the front of the classroom explaining this. And I'm assuming this is like 12 weeks into your automotive course or something. So there's probably a lot of background I'm missing, for one, and for 2,